Welcome, everybody. Thanks for joining. I hope that you're enjoying all the sessions. I know it's a lot of information, but it's also a lot of important information too. So if you're here for this particular session, we're going to go for about 20 minutes on ADF, data flows, best practices, and performance optimizations. This is a huge, broad topic. I'm going to try to cover just some highlights specific to Azure SQL Database, since that is our focus here in today's event. I have at the end of the slides, which we'll share as well, we'll give you a link to the full set of slides with performance tuning and optimizations around data flows and data transformation in ADF all up across all the different, well, I shouldn't say all, but the primary set of connectors that you have within Data Factory and data flows. So I'm Mark Kromer. At the top, there's my information, and along with me is Weihong. He can also answer some questions on chats if you happen to go ahead and put those in there. I'll try to look over as well, see if I can get to those, but we don't have a lot of time and a lot to cover, so I'm going to just start right in, and let's start talking about data flows, best practices, and performance optimizations. And of course, the first thing I can do is advance my slides. There you go. So I broke this down into these different categories. I want to talk about ETL performance with SQL DB. Just to back up for a second, with Data Factory, data flows is the low-code, no-code environment for building data transformation at scale in the cloud. Okay, so we're going to focus on this. I'm not going to focus on copy activity, data ingestion, pipelines, orchestration, and those kinds of things. Whole different set of performance topics. We have some other sessions where that's going to be touched on, and we have a lot of information online on our documentation that we are growing and we're adding to and trying to make easier for you to tweak the performance of your pipelines. I'll talk about transformation optimizations. This can apply to really pretty much any source. It doesn't have to be SQL database or any destination that you write to. I'll show you how to monitor that performance, and then some global settings, best practices, so that you can apply those across the board to your pipelines and data flows. All right, so let's take a look at what you can expect to see when you are transforming data in Data Factory data flows with Azure SQL Database. So this example is a source of a SQL database and a sink as a SQL database. So this could be something like, now remember one thing, with data flows, you can have as many sources as sinks as you want. So you're not limited to just one. But in this case, if you think about a simple data flow with a SQL database in, SQL database out, table size, 74 columns, 887,000 rows, transformed with just a single derived column, we were masking fields. Okay, so this is some data masking. That time end to end was 3 minutes. All right, now we got that performance for almost 1 million rows out of using an 80-core debug Azure Integration Runtime. So debug is that area within Data Factory where you are debugging your pipelines. All right, so you click the debug button. The Azure Integration Runtime as being used was a memory optimized 80-core. Now, in the full deck of slides that accompany this, you will see we have our posted performance engineering stats. So we share that with you with some TPCH data, and you can get some idea of how the different sizes of compute you apply to your data flow can affect the performance of those end-to-end data flows. So recommended settings, this is the third from the bottom bullet points. Recommended settings. Again, recommended settings are, you're going to have to use the typical caveat of your mileage will vary, but this is a good sort of starting point baseline for a general set of settings with SQL database in and out in data transformations and ADF. Set your source partitioning on for a SQL database source. Now I'll tell you what I'm going to do. I'm going to actually flip over to my UI for Data Factory, and I want to show you this. I think it's easier to demonstrate as I talk. So here this is not the one I wanted. I have this one over here called SQL Movies. My source is a SQL database. Under optimized, I am setting the source partitioning. This is under set partitioning source. I have hard coded the number of partitions to 16, and that's just because I know I typically run this data flow with 16 cores of worker compute. Okay. You can make this dynamic. You can use dynamic content, and you can put in an expression, a parameter that you can send it from the pipeline, so on and so forth. So you can dynamically set it. But this is the most optimal way to read data in from SQL database using mapping data flows. Now, notice I also, when you set your partitioning, when you set your source partitions, you're going to want to set a high card partition column. So movie is my primary key, so it's high cardinality. So I've set that for my partition column here on my source transformation. One other thing I do want to say is that on the source options for for Azure SQL Database, we do have isolation level that can help as well with your query time. You will see this third option under here called stored procedure. This is under experimental right now. We are going to be releasing this very soon, so I'm very excited about this as well. If you also want to improve the intake of your data for your data flow, you'll also be able to execute a stored proc and receive the rows out of that stored procedure into your source. All right, so that was that SQL database source partitioning. The current partitioning was set on the derived column and the sink. Let me flip back. I'm going to do a lot of flipping. I'm a flipper. I apologize. Derived column, the optimal way to use derived column in a SQL database scenario in most cases is going to be just let us and let Spark handle the partitioning. You can set the partitioning if you know a lot about your data and you really want to get down into the weeds to optimize this. If you know a lot about your data, then you can use hash partitioning, ranges, and so on and so forth. In most cases, current partitioning is the most optimal for derived column. The same thing with the sink when you're writing to a SQL database. Leave it to current partitioning, which is essentially default. All right, now back on here. Minimum general purpose compute type. We do not recommend compute optimized for production workloads. General purpose has a much higher RAM to core ratio on the VMs. Memory optimized is an even better option for you, but if you want to keep your costs down, general purpose is minimum recommended in production. Now, the last bullet is very important. I believe I'm sure there are other sessions today that talked about the performance of your Azure SQL Database. Very important that we will be throttled in ADF by the scale that you've set on your Azure SQL Database when you're writing. So make sure that you have set the scale. Now you can set it dynamically. Tune it up before you run your ETL processes. Remember, you're going to schedule these pipelines with data flows on a wall clock in most cases. So you can set your SQL database to scale up before that and then scale back down so that you're not paying for the extra scale that you've set during your load from your ETL job. Okay. So some more SQL database timing examples. Left-hand side, 15 gigabyte data sets. CSV into SQL database, 71 million rows in this case, a lot more than a little less than 1 million, 71 million rows. We set to current partitioning using general purpose computes. You will see the different core stratifications on the left, 8, 16, 32, 64. Didn't go higher than 64 for this test, okay? You will see that the stage times increased with or got better. I shouldn't say increased, they got less. They got better as we added more cores. So that scale was pretty evident when you set current partitioning. The stage time, by the way, is the time each transformation step takes in your data flow. The sync is how long it takes to serialize, to persist that data in your database tables. They also increase, notice that, with the core counts as well, all right? So you see that we got for 71 million rows, 64 cores, a total of 44 minutes writing that data into SQL database, and this is including transformation. I'm going to skip the right-hand side. You can always look at that later. That's just another example, and that's actually going the other way. This is SQL DB to CSV. I do want to raise up SQL DW, or what's now known as Synapse SQL Pools, just because we are in the database land here, so I don't want to completely ignore this. I think it's important to call out a few things if you're also using the data warehouse model, because with SQL Pools, it's a little bit different. You will see the sync timing in minutes does not increase, or does not get better, does not decrease. I keep saying increase, does not decrease proportionally with the number of cores that you add. And a big reason for that is because we are using the copy command. We're no longer using polybase inside of data flows. Let me show you this as an example. So I believe I have an example of this over here. Yes, here we go. This sync right here is a Synapse sync. Now, unoptimized, I keep it with current partitioning so I can get the additional partitions. I'm not going to gain anything out of hand partitioning this. But the important thing is to always use staging. So notice we called it generically staging, so we didn't use the word polybase any longer, because as we transitioned into copy command for the database commands, it made more sense to say enable staging. Always enable staging with Synapse. You can enable staging on your reads as well. So when I'm reading from a source, and if I have a Synapse source, I can say enable staging here on the source as well, and you'll see stored procs are going to land for that as well. So Lots of really cool things coming and available to you to make that faster. I told you I was going to go fast. I warned you. So just type your questions into the chat, and we'll try to address those. And you'll have these slides as well, so that you can look at this later. Let's talk a little bit about the transformation timings. Transformation timing is a little bit doesn't necessarily matter what your sources of syncs are. Once you get the data into a data frame, remember, Data Factory data flows and Synapse data flows. By the way, these guidances will work for both Synapse and Data Factory data flows. Same technology, just using different Spark platforms. In ADF, we're going to be using Databricks Spark and Synapse Spark. But the way that you optimize will be the same. And so what you're going to see is that once you get that data from your source into the transformation stages, the data is sitting in memory in data frames inside of Spark. All right. So think about it that way. And so what's going to happen here is, as you increase the core counts using current partitioning, you will see the increase, the decrease in the time it takes to transform the data. This is comparing the window, which is the window transformation for window functions, versus the aggregate in the, with a join. So the reason why you compare window and aggregate a lot of times is because a lot of the aggregation functions, sum, counts, those simple ones, and min max can also be applied in the window, and vice versa. Some aggregation functions are only available in window, like rank, but we have a separate special rank transformation just for scaled out ranking. And that's what we recommend to use for ranks, unless you are needing to build windows of data. Now let's take a look at the differences here between the join and lookup and exist. So join, lookup, and exist are very similar in the sense that they are comparing or combining data from multiple streams within your data flow. And streams in your data flow are just generic streams of data in data frames. So you can combine them from any source. You can create essentially federated farms of data in your flow, in your data flow. And it doesn't matter where they came from. And they can be even ones that you've generated and that you've modified through derived columns. Anyway, the join, the lookup transformation and data flow is essentially a left join with some added goodness in it, some added capabilities in it. And so the left join tends to perform a little bit faster, but the lookup has a lot of features in it that you're going to want. And let me show you what that is real quickly here. I don't think I have an example, so I'm just going to add one real quick to demonstrate to you that the lookup, although it is primarily a left join, does give you the ability to say you want to match on any row, first row, last row. You can then sort that data based on the fact that you want to match multiple rows. So what happens is, when you say that you want to sort that data, let me actually join this with another source to show you that. So now that I'm saying I want to match on the first row, I need to then say what sort order do I want to use for that. If you don't do this in the lookup transformation, you just have to go out and do it yourself manually anyway. So even though, generally speaking, the join itself is a little bit faster than the lookup, you still have some post-processing to do when you do a join. Okay, so just keep that in mind when you see these stats here in this slide deck. This is just a little bit of a more drill down into the left exists in lookup, so I'm going to skip that right here. Alrighty, Uber transformation optimizing in Data Factory. Each transformation has its own optimized tab. You're generally better off leaving that to the default because you can incur reshuffling, which is an expensive process in distributed systems like Spark. Reshuffling can also occur if data is very skewed. So let me show you, because I want to make sure we get to this and I don't want to lose time on it. If you click on the monitoring view and you dig deep into your data flow activities, you can also view this when you debug too. You don't have to, this doesn't have to be just a triggered run. From a debug run, you can see this. Go into your pipeline. When you have your data flow, click on the eyeglasses button down here. For those of you Chicago Cubs fans, you know that's a Harry Carey icon. So when you go into here, you will see that we give you the details of what happens throughout the stages of your data flow. Let me explain a little bit to you what you're seeing here. Each transformation, when you click on it, you will see the partitioning on it. Now notice this is an aggregation right here. So I got one partition because the data has to be brought together from the distributed nodes. As the data is distributed, if you're going to aggregate, you need to be able to bring that to a single point to be able to get the aggregation, which is why aggregates are slow, but also why you see one partition, even though you haven't set that in your optimized tab. I'm caching that. So I'm writing that to a cached sink. So notice that when I access it through a cache lookup, this little icon right here means it's cached data. So throughout your flow, you will see data that's been cached with that icon. Now, here's a key thing to look at when you're looking at the monitoring view. Look on your sinks. There is a set of data down here at the bottom called sync processing time. This is the amount of time it takes to actually serialize or to persist that data in the data store that you're writing to. Notice I got 32 partitions on here, so you can tell by this chart, I, number one, had current partitioning set and had 32 cores of compute on my worker nodes. All right. Beautiful partitioning scheme here. It's very much balanced, very well balanced. You can always look at these skewness and kurtosis to see how balanced or unbalanced your partitions are. Don't lose sleep over that. Only if you are stuck in a extended loop on a transformation should you start to worry about that. All right. But the sync processing time, coming back to that, at the bottom is the amount of time it takes to persist. If this number grows very large, it is because you probably have an undersized SQL database that you need to increase the DTUs on SQL DB? I think it is. You have to increase the scale on your database to be able to break through that. All right. Back to the slides. I already talked about join existing lookups. Window transformation, rank. We have a separate rank transformation that is right here. You go into my edit on my pipeline, go to my data flow. Rank is something that you want to use if you're going to rank data across your entire data set. The window transformation will not scale as well. The window transformation is meant to give windows of data, just like you partition data in Windows using the Windows T-SQL function. Same exact thing applies, all right? And then if you want to do row number, a lot of times some users will gravitate toward row number within window to create unique numbers for rows. No. Use the surrogate key transformation for that instead, much more effective in terms of unique numbering your rows. All righty, I think that's good for that. Let's move on. So I showed you the monitoring. I got to this quickly, so I'm going to skip this. I may come back to it. I have a couple of minutes left. Global configurations, very important point, so maybe just make sure that we touch on this for a minute here. Global configurations will help your performance, but are not panaceas. They are not silver bullets. They will help, but they won't make a. What I'm trying to say is the best way to really affect your performance is to go back to that monitoring view. Let me show you this. In the monitoring view, when you have the monitoring up, look for the sweet spots. Look for the most amount of time being taken. This is, let's go to this bottom one, 4 minutes and 46 seconds, okay? If I want to optimize that, I mean, I'm not sure why I would want to. It's 4 minutes for 4 million rows. I think I'm fine with that. But if you wanted to, you would instead look to here to see where the most time is being spent. And by the way, notice that all the time here in the bottom is that transformation stage, and nothing took very long at all. Everything was in data frames and Spark, and it was super duper quick. It's all writing that took a long time right up here. Okay, almost 3 minutes in this writing. So you'd want to go focus on that and optimize your logic first. Then come back to these global configurations. You can set logging level. Default is verbose, so you get all of that really good view in your monitoring view. You can dial that back. You get less diagnostics, but you can improve your performance slightly. Error handling. Error handling is when you are writing to that SQL database and you want to capture the errors from the driver. So we've got this hooked up from data flows in the sync to error handling for SQL database. So when you're loading your SQL database, if you go over to the settings, and you click on, sorry, my UI is catching up to me. I am talking too fast. You click on error handling settings at the bottom. You can say that you want to make this larger, continue on error, trap the errors, put the errors out to a file somewhere. You can put it into your storage account and we will write the rows. Very, very helpful, important feature in production. A costly feature in terms of performance, 5 to 10% perf hit. So you probably want to test without it. Turn it on when you feel like you're going to have workloads that need to capture and trap those errors. Here's a great one. I'm going to focus on this one for a second here. Run in parallel. Run in parallel is a brand new feature that we lit up. I've yet to do a good blog or a video on this one just because we've been going through a couple of different scenarios with it before I put the real sort of sweet spot out there for you to be able to read up on. On your pipeline, when you're executing your data flow, you will see a option under settings for sync properties called run in parallel. If you just click this, any stream within your data flow that branches off and has more than one sink, you can say run in parallel. The default behavior of data flows is that, I'll show you an example. In this case, I have one cached sink. There's my cached icon, and 2 file syncs. This is coming from SQL Database to file. If I do not set that run in parallel checkbox, these 2 will write sequentially, which means Data Factory has to wait for one to write then the other. So what you get is, in this case, I'm doing something bad, by the way, and I want to show you this. Not bad, but I shouldn't say bad. I'm doing something that's non-performance, but you may still need this as a requirement. I am outputting the single file. The file output text limited in any kind of file, to be honest with you, any kind of file that writes to storage account in Data Factory data flows is super duper fast if you just leave the file name option default. We write the files as the job IDs from the Spark clusters. You may not like that. It gets they look a little gnarly. They have GUIDs in it essentially, but it's super duper fast because it just drops the data as it serializes it, right? Super fast. A pattern we see a lot of users want to do then is want to save it as data that is in a column, which means that you can name the files based on column data or output to a single file, a static literal name. That's fine, but just understand the performance impact of that. It will take much longer to do that for us to go in and change the file names, okay? So I'll finish on this. When you then look at the monitoring, if I say run in parallel, at least I can get some bang for my buck by saying run in parallel. Now those files will write together at the same time to that folder, and they're not blocked by each other. Very important, right? And I'll show you what that looks like. So I had that set on this execution here. And this total execution was 4 minutes end to end. It took 10 seconds to acquire the cluster. It took maybe a minute to do all the transformations. Then notice this first file took 3.5 minutes to write. The second file took 2.5 minutes. So the total time for the data flow should have been greater than 6 minutes, but it was 4 minutes because I said run parallel. So they both wrote at the same time together. All right, I think I'm at time. We wanted to stop around 20 minutes after, so I pretty much made it through. Let me just do one quick check to see if there's any other really important tidbit to give you here. There are a bunch of best practices at the end. I already touched on a lot of these. I was able to throw a lot of this information in there for you. There's a lot in here around integration and runtime optimizations and debug optimizations to be able to have your debug session be very responsive to you while you are using it. But that's pretty much it. So that was Data Factory Data Flow Performance Tuning and Best Practices.